Hello, Professor. This is going to be our video for uh, myself, Matthew Kui, and David Garcia, and our group did the ball and beam. Just to quickly go over what the ball and beam system is, essentially we have a ball and a gear, and this gear pushes up and down the beam in order to control the position of the ball. This is a standard nonlinear problem that's, excuse me, seen in many control systems textbooks, and it's a very basic problem. So these are the parameters that we used to uh, design the system and the plant, and a lot of this is uses University of Michigan and as well as another paper that we found online as a reference. And if we go through all the calculations, our final transfer function is, or our final plant's function is, transfer function of the plant is 0.21 divided by s squared. So now we take this over to MATLAB where we control it. So our first uh, attempt is with PID control. Now with PID control, we went through the iterations and we fell upon a KP of 1, a KI of 0, and a KD of 55. And this is the result that we achieved. Just give it a second to run. Yeah, so you can see that it's a very, very smooth response. Uh, Very quickly, under half a second, it achieves steady state. Um, no overshoot, uh, very, very, very small steady state error, I believe. Yeah, so it's all very clean with PID. PID was by far the nicest way, the nicest way to control this system. Now, our next step was we designed a root phase lead compensator with root locus. So what we did was we took a look at the root locus plots, and they'll come up in a second here. So we took a look at the root locus plots, and uh, my attempt was if I put a 0 close to the origin and attempt to do some pole 0 cancellation and place the pole somewhat a distance away, I would be able to bring this vertical, kind of like right here. See how you see the verticals are much farther. So if I pick a gain close to here, essentially my two poles are now farther away from the axis, and I believe the gain here, we chose a gain of 150. Uh, so that 150 means that the dominant pole is around negative 2, 2.5 or so. Yeah, and that gave us, oops, that gave us this compensator. And you can see that it's much slower compared to the PID control that we had. However, in terms of overshoot and steady state, it's just about as good. So after designing a phase lead controller, we went after a lead controller. And essentially what I did here was I chose gains and I played with the phase margin, how much we wanted to add, and what the W max was. And for the first lead compensator, I chose a gain of 10, addition to phase of 80, and a W max of 5. And once again, and the second lead compensator was a gain of 3, a phase margin of 30 to add, and a W max of 4.5. And that gave us a pretty good response. I'll run it here and you can take a look at it in just a second. Yeah, so it dipped slightly right around here, but it's pretty close to the response of the PID controller in terms of steady state and overshoot. And the PID controller was a lot smoother. This one was a lot more rough. The rise time here is much, much quicker. Um, and these are the figures that I used taking a look at the the Bodhi plots in order to mess with the input, like the alpha and the W max, or the addition to the phase and the gain. So these are the figures that I used. Just taking a look at the gain margin, phase margin of the system. And this was the system with just the first lead compensator. Um, some overshoot here. It's not as good as this one, I would say. So that completes the majority of that's the normal compensator. So now we move on to the state space compensator, and again we would just follow the model, and of course first we check if it's controllable to see if we can actually do anything. And we had a pre-compensator. That's incorrect. Pre-compensator in order to adjust the steady state error. And if we run that, we can take a look. So this is the angle of the beam, and this is the ball's position. It's very, very direct, very smooth. There's no overshoot. Um, there's no steady state error. It's just, boom, it's there. Um, and it's not as fast. It's not as fast as PID. However, it's just about there. And we also have some estimators that we did here. So here we check to see if it was observable as well in order to incorporate observer-based state feedback control as well. And it pretty much gave just about the same plot as before. Excuse me. And we also attempted to do an LQR. However, with LQR, it was choosing more optimized to create a system that's realistic with a linear quadratic region. It wasn't as good as PID, so I would not suggest using an LQR controller in this specific case. We played around with the values quite a bit, and we could not get a decent response that was comparable to PID or just pole placement. Uh, Overall, PID by far took the cake in terms of being able to be implemented realistically, as well as having the nicest response. So we also did an animation, and the reason why we were able to do an animation with just state space was because in state space I was able to take out the angle of the beam. So I would be able to actually model not just the ball, but also the beam. So if we take a look, move this right here. So in order to the animation code is completely, all of it is inside. Um, you run the first section and you run the second section right here, which plots it. And I slowed it down so that way you could see everything moving. And in this case, you noticed in terms of centimeters, we originally had the beam as 100 or as 1, which is 1 meter, and we split that up into 100 centimeters. And so our step response in this case wasn't a step response of 1, but a step response of 0.15 in order to translate to 15 centimeters. And if you take a look, the ball's position is just about at 15 right here. So it's a little difficult to see without any grid lines, but it's just about 15, which correlates with what we saw in the step response when we did state space control. I believe it was this one. Let me rerun it. It's running. Just one moment and it will pop up. There we go. So here's the angle. You saw the beam move up, then down, then it stayed. And the step response very, very quickly. It approached where it was going and it stayed there. It didn't have to go back. It was always moving forward and it eventually stopped. I can rerun it just to reiterate it and just to take another look at it. the ball never stops moving forward until it stops. Yeah. So I ran it a little slow, but I wanted you to be able to see how it was running. If you want to make it faster, this pause button right here, you can just change the value. Let's say we want to change it to 2.5, make it twice as fast as I was running it earlier, and just give it a little bit. It needs to run. Let me see if I can speed it up a little bit. There you go. So you can see how it moved a lot quicker. Yeah. I'll leave that as 5. That way you can see everything. And that completes the MATLAB portion. We did design an app. Let me open that up really quickly for you. Hey Professor, I had to cut the video for a second. My app wasn't loading, so I went back and figured out what was going on, and it's up and running now. And I'll send you this file as soon as this video is over. So essentially, what we did was we went through and we put all of our controllers on a GUI with a user interface. This entire left side you can put in things, you can plot things. This side you cannot touch. So PID controller, here's the suggested values on the right, plot PID. So you can see this is the same response as we had earlier, and this is the step response. So let's say you want to add some KP to it, you want to add some KI to it, you want to lower the dampening, make it 5. And this is probably going to give you something a little bit more unstable. Uh, so it's still stable, but you can see that it has a much higher overshoot, much longer rise time, and still has a good steady state error because we added some KI to it. But if you go back, you can kind of see how uh, it's much nicer when it's like this. Small settling time, rise time, percent overshoot, and steady state error. These are all beautiful values. We also have a root locus lead compensator design. So here's the root locus plot that you can see. Um, yeah, we added a root locus plot so you could kind of see what was going on. And if you changed KC, see, you know, you'd be going farther along the root locus, or you can change the whole location. Let's make this instead of 15, let's make it 1. Actually, let's make it around, let's say 12. Let's go with 10. Oh, yeah. And you can see how the root locus changes too. And it's very nice. So let's go with frequency response. Frequency response, we did lead compensator, and these are the 3 values that we had. I believe this should have been a 3, but let's go back. Or was it a 4? Yeah. Either way, 3, 4, 5 are all very good responses. Just a little more overshoot when you go with 5 versus if you go with 3 or 4. Less overshoot with just pretty much the same amount of rise time. Let's go with 3.5. Yeah, I mean all the responses work just fine. But yeah, this is how you would change it. Let's go with state space. So this is pole placement, just where you want to place your full poles. We have verified that the plant is controllable and observable, so there's no need to worry about that. And we just select where we want our poles to be. Uh, there is an issue here. The issue is that if you have complex conjugate poles, and you don't, if you're not sure, if you don't make them complex conjugate, you're gonna mess up your system. So let's say we have one pole at minus 15 plus 5i and minus 15 plus minus 5.01i, and watch how this pretty much breaks the response. You have some imaginary in your settling time, your overshoot. So just be sure that when you place your poles, you make sure that they're complex conjugates, or make sure they're on the axis. And we also have LQR here. Again, it's this the same we had earlier. And you also had observer-based control as well. Yeah, that's pretty much the same. Yeah, and this completes the app part, the GUI design. I will include these files in as well, and I will pass it off to David Garcia, who will explain his work on Simulink and Simscape. Thank you.
Hello, Professor. I'm going to show you the design of the Simscape model. So it starts here, and I've labeled everything so that I can just use a different file to control it. So from the original world frame, you go to the actual center of the gear. It's a center pin, and that goes to the ability to move the gear. So you need a joint at the center pin into the gear. So the gear and the pin are in the same position, so they're connected to the same frame right here. But then you need to transform from the pin for the ball beam to the pivot pin that's on the radius, or at a certain radius away from the center. And that's what this transform does. That's center pin to linkage pin, CP to LP. And it's the link gear pin. And again, there's a joint because that has to be able to move into the actual linkage between the beam and the gear. And again, everything is named so that I can just use one file to change all the parameters. It has to be able to move into the beam the same way. The ball is just translated on top of the beam. And then the ball has to have a rack and pinion, so you can go back and forward along the beam in different joints here. So that's pretty simple. Once you get the whole thing, you can just turn it into a group. And I call that the plant. And then my controller is controlled from a file. But I just set up a switch case inside the file, and then the switch case is what controls either one of these things. The default is just uncompensated, turns the step response into an angle, and sends it right through the plant. So, and again, just feedback. This is my graph here for my outputs and inputs. And then the actual file that controls it, there are a couple. This one is just to control all the variables in the model. So rather than having to type them in individually, I can change them all here in case something's wrong. And then it was useful to use the opacities while I was making the model, so I can focus myself by making something invisible, and then I can really look more closely at the thing I really care about. Also, I set the colors I can change, so I can highlight what I want to see. And then the geometries are all set here in this one file, as well as the moment of inertia for the ball. And then all the translations were set out here and well documented, because I was losing track of them as I was making this thing. And then I set up a file for defaults for the PID control and for my lead compensator. These are the actual defaults that will be used. And then I can actually use my plant model here. I was able to linearize it. We use a model linearizer, and you can use a step response. You can use a Bode plot. It gives you access to the poles and the zeros through here. And that's where, I don't care about that right now. And that's where this model came from. My transfer function came from there, and then I just solved for my uncompensated system. And this is the state space model that they gave me once I linearized the system. So, and then the actual presentation file is this thing. The first thing it does is it loads up all the variables. So in case you've kind of changed anything or messed around, it just sets them off. You can clear them all this way. And then it lets you select, well, what do you want to do? I want to change the poles and the zeros directly. I can choose that one. And that's going to come down here when I run it. It's going to run this file, because I made everything modular to make it easier to understand and also to kind of check individually. And all this one does is it first loads the defaults, because you're going to mess with them as you try different values. It tells you the defaults, and then it lets you select one, and it makes sure that you actually selected a number for both cases. And then once you've run that file, and then all it does is run the simulation of the model with your new values put in. So if I run it here, this is the default that works. So it's like, oh, I want it to be www. It actually doesn't accept it. So it's like, okay, let's see the default. 0.01. It says the default pole is 5, so I'll give it 5. It might be super fast. I don't know. It'll run a simulation to see. And then if you wanted to, actually, you can come back here. Not this one. And you can look at kind of its response when you set that up. So I'll come back here. Okay, I want to try a different value. Let's try 2 and 20. And still works. And again, you can come back here, see if it automatically updates or not. Yeah, it does. And now it gives you this thing here. It's pretty good. And then the other way to just mess around with it, I said that if you just want to see what happens as you move the poles, setting the 0 by itself and then changing the alpha between them. So selecting alpha tells you the default alpha is 500. And again, I'm pretty sure this one has a check to make sure it's a number. Yeah. Well, that's, again, it's just running this alpha.m file. So instead of 500, I'll say 300. Oh, whoops. And that's what happens as you change. So that's one thing. If you know, you watch it and you know it's made a mistake, because it'll just run off of the pole rather than actually fall because of the constraint of the pinion. It doesn't actually leave the ground. It just kind of moves off the pole, and you know that it doesn't work. I haven't exactly figured out how to solve that in SimScape. But then you can just run it again. It'll clear it, tell me the defaults. I use the default. And I'll try to center it. That's just the same as this one though. So then if I run it again, it's like, okay, what happens if I move it further apart instead of closer? And again, you can come down to the actual model. And you can kind of see where the ball stopped in the model and then start moving again. That's that. Okay. And then the last thing you can do is you can say, oh, let's do a PID control. So it'll give default values here. And they'll say not recommended, KPXC more than 4. Because when I tried to do that, it would go crazy and try to just jump off the post immediately. It says also try PI controller rather than PID controller. So if you want to use it for tuning, you can actually just do a 1, 0, 0 and try to find where it oscillates. For Ziegler-Nicholas tuning, or Nigler's tuning, I don't remember how you say it. And then it's like, oh, it didn't oscillate, and it did ringing instead. So we're trying to find where it oscillates. It's like, okay, didn't like that. Oh, whoops. And then you can just go through again. 3, 0, 0. I believe this one oscillates. Yeah, this one's still just ringing. And again, we're just trying to find out when does it oscillate. Let's go 30. Yeah, you would just keep raising it like that, and then until you can find the once it oscillates, and then you can just come over here. If you want it, go to your scope. If it were oscillating, let's say, just take your scope. Oops, sorry. Take your measurement and try to measure from there to there, whatever they are. Oops. Yeah, so that's it.